Good evening or good afternoon, Dr. Rohi. I'm Abdulakrim Alyhari, and my presentation about race condition and deadlock prevention, multi-threads environments. Here is introduction. We will talk about the context, the challenge, the race condition, deadlock, and the objective. In this introduction, we will talk about modern programs use multi-threading to run faster and feel more responsive. Okay, let's go next. Here, the process and the threads. A process is a full program with its own private memory in simple way, okay? I put a definition here to all of them, doctor, as you see, the process and the threads. And the threads is something, okay, guys. Okay. And the thread is a smaller worker inside the progress. It's something lightweight execute unit, okay, within the process that share the same code, goal, and data. Okay, let's go next. Okay, so here we have the race condition. As you see in this pic, I put a definition to the race condition, okay, and I put the cause of it. In simple way, the race condition happens when two or more threads access a channel, the same data and the same time, as we see here, and I explain it also in a simple code. Okay. The final result then depends on the time, so it can be wrong or random. Let's go next. Okay. Here we have a solution, okay? We use the mutex locks, okay, to protect the critical section. This is ensure that only threads can access the shared resource at the time. And here I explained in a very short way how it works. Also in this diagram, I explain it in a very short way, doctor. Okay, here's the definition of the deadlock. A deadlock happens when threads are waiting forever for each other's lock. A deadlock is a state where a set of threads are blocked forever because each thread is waiting for a source held by another thread. And also here, doctor, as you see, I put a code, use C++, explains everything. And here we have a diagram, and here we have a simple example, the two locks example, where we have thread 1 holds locks A and waits for locks B. Threads 2 holds lock B and waits for lock A. Okay, no one continues, so the program is eventually frozen, doctor. Let's go next. Next, we have the deadlock prevention. Okay, as we see here, we have a strategy, and I explain in a very short way how is it work, and after that, the result of it. The most efficient way to prevent the deadlock in the student's project is to improve a goal locks ordering policy. And how is that works? All thread must lock in static, okay? For example, if a threads need both lock L1 and lock L2, it must always L1 first, then L2. The result, by forcing a constant order, we structurally eliminated the possible of circular wait in this case. Let's go to then. And also here, doctor, we put a diagram explaining the whole process. Let's go to next. Okay, so I will explain this in short. Okay, doctor. Without logs, the shared container ended with a wrong or a similar value that executed. Okay, with a mutex, the container was always correct, but the program takes slightly more time. Okay, without lock undoing, sometimes the program froze as we see in the deadlock before. Okay, with lock ordering, no deadlock, all threads finished normally. Next page. And here we have the summary and conclusion and all the key takeaways for student. So the summary is multi-threading improved performance but introduced complex channel. So here, doctor, a simple summary and conclusion and takeaways for students. Okay, I will summarize it for you in short. Multi-threads is powerful but also dangerous with prepare synchronization. To write safe multi-threads code, we should identify all shared data protected with mutex locks. We used fixed lock order when taking multiple locks to prevent the deadlock. Thank you for listening to me.